Good morning. Lecture 11, Multidimensional Optimization. I gave a brief introduction about optimization in the last class. Uh, in last class was also about optimization. We were just, if we have a function like this, we were trying to, the goal was to find the x opt, which corresponds to the maximum point in the function. I also talked in last class that if you have multiple variables, x, y, z, and a function based on that x, y, and z, many variables, we want to find the x, y, and z such that the function of them is maximized. So that is the general goal in optimization. But then there will be constraints, uh, maybe x cannot be up to a certain point and things like that. There will be constraints also. I'm going to the example in this lecture notes. This example, is read this example. I'm going to also go through it. It's a good uh, example to show what is the practical application of this kind of constraint optimization. So this lecture, this problem is constraint optimization. So if you look at the equation 1, c1 x1 plus c2 x2 all the way up to cn xn, that is what we want to maximize. Assume that c1, c2, cn are known, and then there are certain constraints, like this a1x ai1 x1 plus ai2 x2 all the way up to ai and xn, and then less than bi, and you can have as many as m constraints. So why, first of all, why do we have to solve this kind of, what is the application of this kind of optimization? That's the first question you will have in mind, and the answer is here in this first example. It gives a typical example where this kind of optimization is useful. And I also want to stress one last point before I dive into this example, is that this lecture is, even though the title didn't say it, this is multi-dimensional optimization. Everything is linear. That means the function is linear. Now this is a linear function, so that's a linear function. The constraints are linear. So if this is not linear, like think about optimization in the previous lecture, it was not linear and there were no constraints. This becomes difficult when the function is not linear. It becomes difficult, and we are not at this undergraduate level. We are not really uh, focused on that. For example, if you go to graduate school, there is one course just on optimization, to give you an idea. Though that optimization course at the graduate level will talk about all kinds of non-linear optimization problems. So anyway, so here we are going to study about a simple linear optimization problem under linear constraints. So the solution is in the form of simplex method. So the simplex method has a special meaning that it is a set of rules that that is used uh, to solve uh, this linear programming problem. So um, that's what we will do. We will just learn about that method. So that's a goal in this lecture. We are going to learn about this particular method. Okay, so example 1 says, please read it. It says that it explains a fictional problem where you have a gas processing plant. We have two types of gases. One is regular, other one is premium. and then there is a capacity of how much gas you get. Uh, sorry, how much you receive. So that is only, you can only process 77 cubic meter in a week. And then so the raw gas you get is 7 meter cube for the regular, and the premium, meter cube per ton, that is 11 for premium. And then the production time, that is 10 for regular and 8 for premium. And the storage is 9 tons for regular and then 6 tons for premium. And then the profit you get is you get 15K per ton on the regular, and then 175K per ton on the premium. So I'm just looking at the table and reading them, but that is, if you read the paragraph, it says a realistic problem. Our goal here, so first of all, let's call x1, we are going to assign variable x1, we will call it regular, x2 we will call it premium, and then we will assign after that we will just, what we read here in this problem, this is a real world problem, and then we will just put them into an optimization problem very similar to what was described in equation 1 and 2. So first of all, what we want to maximize, profit. The profit is for 150 times x1, whatever the amount we produce in regular, plus 175 x2. That is the profit. We want to maximize that. But each has its constraints. For example, 7x1, I am looking at this equation here, 7x1 plus 11x2 is less than 77. That is based on the first constraint. This next one is, I have it wrong here, and the next one is 10x1 plus 8x2 is less than or equal to 80. So that is based on the second on the table. And then we know that the storage capacity is x1 less than 9. So in summary, the problem can be reduced as it is shown here. So we have an objective function that we need to maximize this 150x1 plus 175x2, where x1 denotes regular gas and then x2 premium. Now we have all these constraints shown here. The first constraint, 7x1 plus 11x2 should be less than 77. Second constraint, 10x1 plus 8x2 should be less than 80, less than or equal to 80. And then the limit on the regular gas is x1 less than or equal to 9, x2 less than or equal to 6, and then since these are real quantities, they cannot be negative, so x1 and x2 should be greater than or equal to 0. So the question is, what is the x1 and x2 quantities that will maximize the profit? So this is the profit. So which values will maximize the profit? So there are two types of approaches we are going to study. One is the graphical approach, the other one is the linear programming method. So first I'm going to go through the graphical approach, then we will study the linear programming approach. As always, you will see that graphical approach, you cannot program it. A human needs to see the graphs and see where the maximum is, whereas the advantage of the linear programming approach is, for any numbers, for any problem that is formulated in this fashion, it can be solved using a program. So that is the goal. That's the ultimate goal, to write a program to solve this problem. Okay, so first we are going to solve this graphically, and even before that I'm going to like put each of these constraints on the graph. That's the inequality. So let me find out where the region of convergence, where we can change the variables based on the constraint. So I'm going to show how the first constraint is placed on the graph. So let's consider, instead of x and y, uh, we have x1 and x2. So that's x1, x2, and the goal now is to show this constraint on the graph. So 7x1 plus 11x2 should be less than 77. What is the region? So there are two important points here. When x2 is 0, so I'm going to just write it secretly here. X2 is 0 means what is the cutting point? X2 is 0 means x1 is 11. And if x1 is 0, so that is 11. So let me put a rough scale here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 11, 12, 13. Okay, so that is one point. And the other one is when x1 is 0, x1 is 0, x2, x1 is 0, x2 is 7. 7, so that is another point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 7 is here. So that is the first one. So that is the first uh, region. So we want the variable x1 and x2 to be less than, because 7x1 plus 11x2 should be less than. So that all of that area, that is this region, is 7x1 plus 11x2 less than 77. And we also know that x1 x2 is greater than 0. So this whole, I did not uh, show all of them, but all this region here is x2 greater than 0. Similarly, all these region here, all this region is x1 greater than 0. So these are all our constraints. Look, x1 greater than 0, x2 greater than 0, this. So I have finished all of that, and I also have, let me finish the next one. 10x1 plus 8x2 less than 80. I will use a different color for that. How about this? 10x1 plus 8x2 less than or equal to 80. Similar to before, I'm going to find the critical points there, the intersections on the x1 and x2 axis. So when x2 is 0, x1 is 8. So 8 is, let me use black. Okay, x1 is equal to 8. When x1 is 0, x2 is equal to 10. These are the 2 points. So 8 is here, and then 10 is here. So let me connect them. Okay, so that will be 10x1 plus 8x2 less than or equal to 8. So all the constraint, I put it there. No, wait, x1 less than or equal to 9. So that is another constraint. x1 less than or equal to 9. So that is another constraint, x1 less than or equal to 9, and then x2 less than or equal to 6. So that's here. X2 less than or equal to 6. So when I look at this, so this is our region of convergence. Let me highlight it. Use this color and maybe a bit bigger. So our region of convergence is here, here, here. So this is where we are looking for a solution. So the feasible solution needs to be found here within this constrained region. So this is where we are going to find the solution. So which x1 and x2 will give the highest value of profit, which is 150 x1 plus 175 x2. So once you define the region of um, constraints, then all you have to do is plot that function 150 x1 plus 150 x2 and see when that is maximized. So it would be nice if you can draw this to scale. I kind of did that, but roughly, if you just use a scaling paper, and you will see that 150 x1 plus 150 x2 is going to be, this is how it is going to be. It will go to all these points, and the maximum point. So these are all different version of 150 x1 plus 175 x2, and then the maximum will be, you can, that I messed up a little bit. This is the point, the maximum. Maximum. So that is in my graph. That's somewhere here. So that if you see what is the maximum point, that will come as x1 is 4409 and x2 is 3509. That's not a whole number, but that is how you will find. So that is the maximum x1 opt, and this point is x2 opt, optimum value of x1, x2. So that is for that value of x1 and x2, the profit is maximized. So that is the graphical solution. Now we are going to, so it is also in the lecture note, take a look. But next we are going to do the simplex method. So solving this problem using a different approach. Okay, we are going to solve this example 3, a different problem, using the simplex method. So now the previous example gave an idea of what this means in real world. Now we will only focus on the equations and how to solve the steps to solve them, and our goal is always to program this as always with the other examples, previous lectures. So maximize this function 15x1 plus 6x2 plus 25x3 subject to all these conditions: x1 plus x2 plus x3 less than or equal to 5, x1 plus x3 less than or equal to 3, x1 less than 4, x2 less than 1, x3 less than 2. And also all these variables should be greater than or equal to 0. So let's see how this is solved. The first step is to write the objective function, and then write all the constraints in a form that, in an equality form. So this is all, instead of less than or equal, you see equality, equal sign. So that is because we added variables. The original constraint was x1 plus x2 plus x3 less than or equal to 5, but I added a variable s1 and call it equal to 5. So these variables are called slack variables. Slack variables. So with this, I'm going to introduce few steps to solve this problem. So I'm going to just, already have the tables prepared. So we are going to enter these in tables, and then we are going to do a certain steps to understand how this is solved by hand. Then we will program it. Okay, in this table I have filled all the data from the equation here. So so all the right hand side, so we will call this z. That is what we want to maximize. So that's the first equation comes here. So first of all, we have the variables here, x1, x2, x3, and all the 5 slack variables. And this is the solution. That is the right hand side of the equation. For it is slightly different for the objective function. We will put 0 first, but we will move from there. So 15, 6, and 20, 25 come from here. 15x1 plus 6x2 plus 25x3 is equal to SAT. That is what we want to maximize. All the slack variables are 0 for that. These are, then the remaining ones are the right hand side of constraints. Right hand side of constraints. I will go one by one. For example, if I look at the first constraint, it is 5 is equal to x1 plus x2 plus s1. So if we go by 5 is here, then 1x1, 1x2, 1x3, 1x1, everything else is 0. Same, we look at the other equation, 3 is equal to x1 plus x3 plus s2. So 3 is equal to x1, there is no x2, so 0, x3, there is no s1, s2, and everything else is 0. Similarly, all the remaining 3 equations, we can put it in the table. So having filled the table, now we have to do two things. First, we need to find what is the entering variable. So which means that one of the variables is going to enter here, on this side. Right now we have all the slack variables, but we won't. Based on a criteria, some x1 and x2, x3 will come there, and then we will repeat the process. So let's follow this. What is the entering variable? That is the look at the first row and whichever is the corresponding to the largest coefficient there. So 25 is the largest in the first row, so x3 is the entering variable. X3 is the entering variable. Now we decided, we know that this is the entering variable. So this column becomes important now. So this column is important now. What we do is we take that column and then take the first column, solution column, and then we find out of these S1, S2, S3, S4, and S5, which one is the leading variable. To do that, we take the ratios of each of the ratios. So first, for S1, the ratio is 5 over 1. For S2, the ratio is 3 over 1. S3, the ratio is 4 over 0. S4, the ratio is 1 over 0. And then S5, the ratio is 2 over 1. So let me put those values: 5, 3, infinity, infinity, 2. So we have to look for the minimum. So this is the minimum. the leaving variable is 2. So now we are going to use this information to repopulate the table. So after we select the entering and leaving variable, so we selected S5 as a leaving variable. So this is called the pivot. So that's a pivot to element. That's pivot. Now what we want to do is we're going to do some row operation to eliminate these. We want to make all of them 0. So that is the next step before we go to the next tableau. So if you look at this, I already have the labels for each rows. Each row has a label. So this is row 1, row 2, row 3, row 4, row 5. So we'll call them based on that, based on the pivot element. Now we want to do some row operation to make all of them 0. So what are the row operation? It is R1, if you wanted to make it 0, so we will use the pivot element always for the row operation. So these are the row operation that we will do. Let me put a title there. So these are the required row operations. That is R1 is R1 minus 25 R6. That will make that element 0. R2 is R2 minus R2 minus R6, and then R3 minus R6. So these are the required operation that we will do. So after we are done with that, I will go, we will just go to the new, we will go to a new table where we know this is the entering variable that comes here. So the new table will have x3 at this position. So I want to show how each row operation is done. So when you do the first row operation, the new numbers, the row 1 will get new numbers when you do the first row operation. When you do the second row operation, some of the numbers will change, some of them won't, based on the operation that is mentioned. And then this row will have it. So those are the 3 rows that is going to change. So these new values will go to the table here. So in this table, now we have to find what is the entering variable. Entering variable, to find that, we go to the first row and find the largest number. The largest number is x1. So that is why x1 is the entering variable. To find the leaving variable, we will go to the first column and the column corresponding to the entering variable, and then we will do this ratio 301, 101, 401, 100, and 200. That comes to 3, 1, 1, infinity, and infinity. So that is not 1, that is actually 4. So the smallest one is S2, so that is leaving. So S2 is leaving, and so obviously X1 will come here. So what are the row operations? The row operations will be, so that's a pivot element, first of all. Wait a second, pivot element. And the row operations, so we will do the following row operations. R1 is R1 minus 15 R3, R2 minus R3, and then we also have a non-zero value at R4. R4 is R4 minus R3. So we will, now the process is going to repeat. We finish this row operation, go to a new table, and then find the entering variable, find the leaving variable, and then we have to do it again. So when do we stop? We stop when all these elements are negative. Of these row are negative is when we will stop. Okay, so having explained how these steps works, now I will just go back to the lecture notes to this is the same table that I worked so far. So I was here, so we did this and then we found out the leaving variable was s2, so that is going to be in the next table. We will have x1 replacing x2 because that was the entering variable, and then so we are here at the third table, and then at this point we will look at the first row and find out which one is the entering variable, the largest coefficient, that is here x3. So x3 is going to enter. So we will do the ratios here. So x3 means that is a row that is of concern. So we will do all the ratios and then we find that x4 is leaving, and then sorry x2. So I had it wrong. So x2 is leaving. X2 is the entering variable. So when you do the ratio, x4 is going to be leaving variable. So that is the pivot element, and then we have to do these two row operations. When you do all of that, you will end up with this table. So you will see that all elements in the first row are negative. That means we can stop. So when you stop, so what is the solution? So 71 is a negative of the value that there. 71 is the maximum solution. So 15x1 plus 6x2 plus 25x3 is equal to 71. That is the maximum value for values for x1. x1 is 1, x2 is 1, and x3 is 2. x1, x2, x3. So that is the solution for this optimization problem. So that's an example of how linear programming is done. You can see, the main thing here is finding those entering and leaving variables and doing those raw operations. So this can be programmed once again in a naive way, because if there are some zeros, or it is only a basic concept is described here. There are softwares, MATLAB and Excel, and all of them have softwares. Most of the time, when you go about solving a practical problem, there might be problems about divide by zero, what to do with that. When there are two equal coefficients here, what to do with that. All of that will be taken care of. At least here, that is not introduced. So at the software level, there's a very elaborate solutions for this. So most of the time, we will be using existing software rather than writing a program. But it is important to know what is the basic. Very similar to in math and all these differential equations and all of that. We want to know the goal of this course is to teach some basics, and this is definitely a basics of how to solve a constraint optimization problem, linear constraint optimization problem, and that is an approach to that problem is a linear programming. How it works is what was taught here. So there are two examples here, a couple of examples in the lecture note. I'm going to assign one of them as a homework so that you can practice. And then if you want, you can also program them. I'm not sure that it's going to be the lab, because for the lab I was going to assign probably Gaussian elimination, but it probably is not a bad idea to assign this linear programming as, or maybe project, but I will think about that.